So this is my lab report for our lab 3, which is circuits. To introduce this lab, so our purpose was we were designing a circuit with our group that followed both the energy conservation and current conservation principle using these multimeters right here. The fundamental principles, I kind of gave it away already, but we're using energy conservation and current conservation in this picture right here. It's just kind of a preview of our original circuit design with resistors in series. And this link is a link to the instructions for the lab if anybody wants to follow along. So resistors in series, part 2.1. So right here we were prompted with this diagram, which we have two batteries. Both are 1.5 volts, so total should be about 3 volts. Current comes out, goes to ammeter number 1, goes to 2 resistors in series, and then goes to ammeter number 2. And so that's the circuit we tried to design right here. So we've got this little wire connecting our two 1.5 volt batteries. We've got the current going through this wire right here into ammeter number 1. It then goes into, we didn't connect it for this picture, but later on we did, connects to resistor number 1, which has 47 ohms. Another wire connects this resistor to resistor 2, which has 100 ohms. Then it goes all the way to ammeter number 2, where it could be measured, and then right back into the negative side of the battery. So using the VIR equation, we can calculate the theoretical current that we should measure on these two ammeters. So we have that the current is equal to 3 volts total over 147 ohms total, and that should give us about 0.02 amps. So our ammeters actually ended up reading 19.3 milliamps, which is 0.0193 amps, and I'd say that's pretty close to 0.02 amps to our theoretical. Now, if you reverse the connection, that ammeter will read negative 19.3 instead, because that means that you're going against the current flow, so it would be the opposite sign. So when we were prompted in 2.3 to convert this ammeter, this first one we had, to a voltmeter, we have that it reads 3.1 volts. And that makes a lot of sense, right? Because you have around 3 volts coming out of these two batteries right here, and they haven't met any resistance quite yet. So you still have a strong about 3 volts coming through this voltmeter before it has to go through some resistance. Now we have where we want to measure the delta V, the change in potential across each resistor. So we remove the voltmeter in order to do that. So over the 47 ohm one, we found that it was a loss of 0.9 volts. And across the 100 ohm one, we found that it was a loss of 1.9 volts. And when you add these, the actual sum for our experiment was a negative 2.8 volts, whereas the theoretical should be negative 3.1. And so there's kind of two possibilities here. It's possible that these resistors are weaker, the ones we're using, than they should be, because they're still about 0.3 volts traveling at the end of our circuit, even after it passes both resistors. But another case could be that there's resistance in the wires and the batteries that actually makes up for that 0.3 volts. This is a graph we have. So starting going through the batteries right here, they get up to about 3 volts right here. And then right here we have that through the 47 ohm resistor, we drop about 0.9 volts to 2.1. Then through the 100 ohm resistor, we drop even more to about 0.3 volts total, which was, how we calculated it through the experiment. Last part, for the resistors in series, we're prompted to replace the voltmeter with an ammeter and put it in parallel with our 100 ohm resistor. And we measured through the other ammeter, we got about 48 milliamps. Now next, for this portion, we had an RC circuit. So this looked like we still had the two batteries right here, and then they connected to a capacitor which could charge, and then disconnected to a resistor, so which in this case was like an 8 ohm or a 30 ohm light bulb. We used both for this experiment. So what would happen when we connected the 8 ohm bulb to the circuit? So it ended up dimming over time, but then when you disconnect the battery, the bulb will light up due to the charge that has accumulated in the capacitor, but then it dims over time still because the capacitor has a finite charge. And if we do the same sort of process with the 30 ohm bulb, it's the same thing as these two parts. It's just that there is more resistance. So for example, we calculated the time. So for a 30 ohm, about 80 seconds to charge, only 30 seconds to discharge until we saw the bulb dim again. So 13 seconds to charge, but then only 9 seconds to discharge when we saw the 8 ohm bulb dim again. Some sources of error for this lab. First off, like I said before, our resistors could be old, could be decayed. Second thing is our group members might have not been very still with the multimeter, so it might have interfered with our voltmeter and ammeter readings. And lastly, we could have connected the multimeter to the wrong portion of the circuit, as we didn't mean to. Lastly, our final discussion question for this lab. So what if we charged the capacitor, but there was no resistor, no light bulb in that circuit? So theoretically, our model predicts that the capacitor like almost instantaneously charges if there's not a resistor in place, because the time would be about zero. But this probably isn't likely in real life, as I think this could probably blow up the capacitor, and there's always some internal resistance in the batteries and wires that's inherent anyways.